the Daily Science podcast from NPR. To solve the problem of how to redirect lightning, researchers first need to understand what lightning is. The easiest way to think about this is if you've ever scooted across a carpet with fuzzy socks on, and then you shock yourself on a doorknob, or purposely shock your sibling. There's a little spark of static electricity. And basically one of two things is happening here. Either you're accumulating electrons, those negatively charged subatomic particles, on yourself, or electrons are being ripped from you, making a part of your body a supercharged thing, where before you were more or less neutral, no big charge imbalance. In either case, your body wants to be balanced again. So that imbalance of electrons results in these subatomic particles literally jumping off your body or to your body from somewhere else. That is mini lightning you see as you shock yourself. As for what that means for lightning out in the world, that's what's happening to the clouds in the sky. Water and hot air currents move those electrons around.
Lightning happens when you have formation of huge clouds in the sky with a charge inside the clouds. And actually, the charge appears in the clouds when you have a big movement of particles of water in the sky. And because some space are hotter and some are colder in the skies, you have some air that goes up and some air that goes down, and it makes friction. And it's like when you touch the wool.
The wool sweater.
When you touch it very fast, you can make electricity.
The clouds become charged, and electrons either want to travel to the ground or connect with a positively charged cloud. That's lightning. And while it's very unlikely that lightning will hit a person, every year it damages trees, buildings, and delays many flights. So what's used now to redirect lightning away from buildings is a lightning rod. It's a pointy piece of metal that acts as a conductor, letting electricity flow through it. And it's connected to the earth, or grounded. Since the rod is grounded, it can attract lightning and siphon off excess charge from the clouds, reducing the likelihood of lightning. Aurélien says that there's technically another method that successfully redirects lightning: rockets.
In the end of the 20th century, the fact to use rockets with an electric wire attached to the rocket. So if you send a rocket with a very long wire behind the rocket, 100 meters or even more, the rocket with the wire will start to be charged in the presence of the electric field created by the lightning cloud, and it will induce a lightning and guide it along the wire. So you can have a guiding of the lightning like this.
But this rocket approach has a lot of downsides.
It requires a very precise timing to shoot the rocket, and also it can only work one time. So it was never really considered as a protection for lightning because it's too expensive. It's waste and it can fall, you don't exactly know where. And you have to retrieve what remains of the rocket. But this is basically what we want to do with the laser, but with something that doesn't fall down and that you can use continuously when you need it.
So, okay, lightning rods cover too small an area, rockets are impractical, enter those high-powered lasers. In 2021, Aurélien and his team successfully used a laser to redirect lightning for the first time ever. This is how it works. The laser shoots a beam into the air, and it forces molecules in the air to undergo ionization.
In every molecule in air, you have nitrogen and oxygen. You have some electron around the molecule. And if you send energy on this molecule, you can detach some of this electron outside. And then the electron can go everywhere.
They used a laser that pulses 1,000 times a second, which basically creates a column of air with all these free electrons, turning it into a giant lightning rod. This experiment was done on a remote Swiss mountain, where a telecommunications tower is struck roughly 100 times a year.
So on the Swiss mountain, the difficulty of this station was that it's not accessible by road. So you need to use a gondola to go there, or to use an helicopter. And so we used the gondola for most of the equipment, but for that we had to design a laser that would be able to be splitted in small parts to fit in the gondola.
It took 4 months to install everything.
So we had to separate the laser in several parts, to put it in the gondola, and to make the laser in one part again on top of the mountain.
It was an exciting moment because this laser, it's a fulfillment of a decades-old idea. But a successful test wasn't possible until recently due to a number of things. First, the lasers had to get more powerful.
We choose a laser technology that is able to shoot 1,000 laser pulses per second. So it's a big increase compared to all the experiments that were done before, because they were only shooting 1 shot per second or 10 shots per second. So we have much more chance to catch the lightning when it's developing and to guide it during its propagation.
Second, it turns out it's really hard to predict where lightning is going to be to test these lasers. Aurélion's team found a solution for